Okay, let's get into it. Fine, let's start. Number 10. The Cosmic Cocktail Cloud. Picture the center of our galaxy, 26,000 light years away, past the crowded star fields, past the dust lanes, right near the supermassive black hole that everything orbits. And sitting there, in that violent neighborhood, is a cloud. A vast one. Hundreds of light years across, made of cold gas and dust, slowly collapsing under its own weight to make new stars. Its name is Sagittarius B2. And here's the part that nobody quite believes the first time they hear it. That cloud is full of booze. I mean that almost literally. Inside Sagittarius B2, there are staggering quantities of alcohol. Methanol, ethanol, the kind of molecules you would find in a distillery. And floating in there with them is a molecule called ethyl formate. Now, ethyl formate is interesting for a very specific reason. On Earth, it's one of the compounds that gives raspberries their flavor, and it happens to carry a faint smell of rum. So somebody, somewhere, did the obvious thing and put those two facts together. And that's where you get the famous line, the one you've probably heard before. The center of our galaxy smells like raspberries and tastes like rum. Now let me be the friend who tells you the truth before someone else oversells it. You could not actually drink this cloud. The alcohol is real. The quantities are genuinely enormous. But it's spread so thin across so much space that in any given handful of it, there's almost nothing at all. It's a near-perfect vacuum that just happens to have a cocktail's worth of molecules drifting through it. You'd need to filter a volume of space the size of a planet to get a single sip. But here's the thing. The raspberry rum story isn't really the interesting part. It's just the hook that gets people in the door. The actual discovery, made back in 2009 by a team using a 30-meter radio telescope in the mountains of Spain, was that this molecule was there at all. Because ethyl formate isn't just a flavor. It's a member of a family of molecules that sit on the chemical road toward amino acids. The building blocks of proteins. The building blocks of us. So this cloud near the galactic center isn't a bar. It's a chemistry lab. A cold, dark, slowly turning lab where the universe is quietly assembling the kinds of molecules that, somewhere, sometime, might become alive. The raspberry smell is a coincidence. The fact that complex organic chemistry is just sitting out there in the dark, waiting, building itself out of starlight and dust, is not. And we've barely opened the door. Hundreds of different molecules have been found in clouds like this one, and the list grows every year. The galaxy, it turns out, is not a sterile place. It's stocked. Number 9. The planet where it rains iron. 640 light years from here, in the constellation Pisces, there's a planet that should not be allowed to exist. Its name is WASP 76b. It's a gas giant, bigger than Jupiter, but it orbits its star so close that a single year there lasts less than 2 of our days. It's so close that it's tidally locked. One face always points at the star. One face is always turned away into the dark. And on the day side, the temperature climbs past 2,400 degrees Celsius. That is not very hot. That is hot enough to do something genuinely strange. At that temperature, metal doesn't melt. It boils. The iron in that planet's atmosphere, the same iron that makes up the core of our own world, turns into vapor. It evaporates, like steam off a kettle, and rises into the sky. Then the winds take over. Brutal winds, screaming across the planet at thousands of kilometers an hour, dragging that iron vapor away from the blazing day side and around toward the night side. And on the night side, it's cooler. Not cool. Just cooler. Cool enough that the iron vapor does what vapor does when it cools. It condenses. It forms droplets. And it falls. It rains iron. Molten metal falling out of an alien sky. Now, how do you possibly know that? You can't see this planet. It's a smear of dimming light 640 light years away. And the answer is one of my favorite pieces of detective work in modern astronomy. In 2020, a team led by an astronomer named David Ehrenreich pointed a spectrograph called Espresso, mounted on the Very Large Telescope in Chile, at this planet, and they tracked the chemical fingerprint of iron in its atmosphere as it rotated, and they found something odd. They could see iron vapor on the evening edge of the planet, the side rotating into night. But on the morning edge, the side rotating back into day, the iron was gone. Vanished. Think about what that means. The iron is present in the evening. It's absent by morning. Something removed it during the night. And the only thing that fits is this. Overnight, on the dark side, the iron rained out of the sky. It fell. So by the time that air comes back, around into the morning, it's been wrung dry. The missing iron is the rain. To be fair, some scientists have pushed back on the word rain and argued the chemistry might be a little more complicated than a simple downpour. The iron vapor itself is not in doubt. The exact mechanics still get debated, but the picture is hard to shake. A world where the evening sky is full of vaporized metal, and the night washes it away in a storm of molten iron, and the morning comes up clean, and it all begins again. There are places where the weather forecast is just one word, repeated forever. And on WASP 76b, that word is iron. Number 8. Diamond Rain. Let's come home a little, back into our own solar system, to the two planets almost nobody thinks about. Uranus and Neptune, the ice giants. Pale blue, far away, cold, easy to forget. We've only ever visited them once, with a single passing spacecraft, back in the 1980s. And underneath those calm blue cloud tops, something extraordinary might be falling. Here's the setup. These planets are full of methane. Methane is a simple molecule, one carbon atom holding hands with 4 hydrogen atoms. Up near the surface, it's just gas. But as you go down, the pressure climbs. And it climbs. And it climbs. Until thousands of kilometers deep, it reaches a level that's almost impossible to picture. Millions of times the air pressure you're sitting in right now. And under that kind of pressure, the methane can't hold itself together. The molecule gets torn apart. The hydrogen goes one way, and the carbon, set loose, gets squeezed so hard that it does what carbon does under extreme pressure. It crystallizes. It becomes diamond. And those diamonds, denser than everything around them, begin to sink. They fall, slowly, through thousands of kilometers of hot, dense fluid, drifting down toward the core like a glittering, silent hail. It rains diamonds inside Neptune. It rains diamonds inside Uranus. Maybe for billions of years. For a long time, that was just a beautiful idea. A calculation on a chalkboard. Until 2017, when a team of physicists decided to actually make it happen. And this is the detail I love. They didn't use some rare exotic material. They took a thin sheet of polystyrene, plastic, the stuff disposable cups and packaging are made of. Because polystyrene is made of hydrogen and carbon, the same 2 ingredients as the methane inside the ice giants. They put that plastic in front of one of the most powerful X-ray lasers on Earth at a lab in California, and they hit it with a shockwave. For the tiniest fraction of a second, that sheet of plastic experienced the pressure and the heat of a place 10,000 kilometers below the surface of Neptune. And when they looked at what happened, they saw it. Nearly every carbon atom in that plastic had snapped together into tiny diamonds. Nanometers wide, but real. Diamonds made from a disposable cup by squeezing it the way a planet would. So it's true. The thing that sounded like a fairy tale, planets where it rains diamonds, is as real as the chair you're sitting on. And those diamonds aren't small fairy tale gems either. The models suggest that over the lifetime of these planets, the diamond rain could build up, sinking and pooling, possibly forming layers, maybe even oceans of liquid and solid carbon down near the core. There may be more diamond inside Neptune than has ever been dug out of the entire Earth, falling quietly in the dark where no one will ever hold it. Number 7. Helium Rain. Stay close to home for this one, because we're going to Saturn, and we're going to solve a mystery that bothered scientists for decades. Here's the mystery. Saturn is too warm. That sounds like a strange thing to say about a planet 1 billion kilometers from the Sun, where the cloud tops sit at around minus 140 degrees Celsius. But when you actually do the math, when you work out how much heat Saturn should be giving off based on its size and its age and how long it's had to cool down since it formed, the numbers don't add up. Saturn radiates more heat than it should. It's putting out more energy than it receives from the Sun. So where is that extra heat coming from? For a long time, nobody could say for sure, and then the answer turned out to be hiding in the rain. Saturn, like Jupiter, is mostly hydrogen and helium. Near the surface, those two gases mix together happily, the way they always do. But go deep enough into the crushing pressures and the strange conditions of the planet's interior, and something changes. Down there, the helium stops wanting to mix with the hydrogen. It's a little like oil and water. The helium pulls itself together into droplets, and helium is heavier. So those droplets do the obvious thing. They fall. It rains helium inside Saturn. A slow, invisible drizzle of liquid noble gas, sinking through an ocean of liquid hydrogen, falling toward the core. And here's the beautiful part, the part that closes the case. When something heavy falls through something lighter, it releases energy. Friction, gravity. The simple act of sinking. Each droplet of helium, as it falls, gives up a tiny bit of heat. Multiply that by an entire planet's worth of helium, falling for billions of years, and you get exactly the missing warmth. The reason Saturn is too hot is that it's been raining inside it since before the dinosaurs, and the rain itself is the furnace. And in 2021, scientists managed to back this up in the lab. They took hydrogen and helium, squeezed it between diamonds, then blasted it with a dozen giant laser beams to recreate the pressures and temperatures deep inside the planet. And they confirmed it. Under those conditions, helium really does separate out. The rain is real. The same process is happening inside Jupiter, with a twist. There, the falling helium drags another element down with it, a gas called neon, pulling it out of the upper atmosphere. And sure enough, when we measure Jupiter's outer layers, the neon is missing, carried down into the deep by a rain we will never see. So the next time someone tells you it rains water, and that's normal, remember Saturn. Somewhere out there, a planet has been raining a noble gas for 4.5 billion years, and that quiet, endless rain is the only reason it's still warm. Number 6. The sea of the wrong liquid. There is exactly one other place in the entire solar system where you can stand on a shoreline and watch liquid lap against the land. One other world with rivers and lakes and seas. It is not a planet. It's a moon. Saturn's largest moon, Titan. And everything about it is almost right and completely wrong. From a distance, Titan looks unsettlingly like home. It has a thick atmosphere, thicker than Earth's, so dense you could almost flap your arms and fly. It has clouds. It has weather. It has rain that falls from those clouds, gathers into rivers, carves out valleys, and pools into broad, dark seas, hundreds of kilometers wide. We've mapped them thanks to the Cassini spacecraft, which spent years circling Saturn and peering through Titan's haze with radar. They even have names. Ligeia Mare, Kraken Mare, the biggest, hundreds of meters deep in places. So you've got an atmosphere, clouds, rain, rivers, shorelines, seas, It sounds like Earth, and then you look closer, and the whole picture turns inside out. Because the temperature on Titan's surface is around minus 179 degrees Celsius. At that temperature, water isn't a liquid. Water on Titan is rock. It's so cold that the bedrock, the mountains, the pebbles on the shore are all made of frozen water, hard as granite. So if water is the stone, then what is the liquid? What's in the rivers? What fills those seas? Methane and ethane. The stuff we burn for fuel here on Earth. The stuff in your gas stove. On Titan, it's so cold that it pours like water. The rain that falls from Titan's clouds is methane rain. The rivers are rivers of liquid natural gas. The seas are seas of the kind of fuel we'd pump into a tank. An entire weather cycle, complete and elegant, running on the wrong liquid at a temperature that would kill you before you finished a single breath. And then there's the sky. Titan is wrapped in a thick orange haze, the reason you can't see its surface in ordinary photographs. That haze is made of something called tholins. Tholins are what you get when sunlight hits the methane high in the atmosphere and starts breaking it apart and recombining it into bigger, messier organic molecules. A sort of tar, a reddish-brown organic gunk that forms up high, then drifts down and settles over everything, coating the dunes, sinking to the bottom of the seas. It rains sludge on Titan. Slow, soft, organic sludge. But here's the thing that keeps scientists awake. All of that, the tholins, the organic chemistry, the liquid, the energy, those are the raw ingredients that interest people who study the origin of life. Titan is cold, alien, lethal, and it is also one of the most chemically rich worlds we know of. There's a mission on the way right now, a nuclear-powered drone called Dragonfly, that's going to fly across Titan's dunes and sample that chemistry directly. A world that looks like Earth's twin in a dream, and in the dream, everything is made of the wrong thing, and the air rains tar, and the sea would freeze you solid. And we're sending something to go look at it. Number 5. Liquid metal hydrogen. Hydrogen is the simplest thing there is. One proton, one electron. It's the first element, the lightest element, the most common substance in the entire universe. About 3/4 of all the ordinary matter in the cosmos is hydrogen. It's the stuff stars are made of. It's gentle. It's light. It's everywhere. And inside Jupiter, it becomes a monster. Jupiter is enormous. You could pour all the other planets in the solar system into it and still have room. And almost all of it is hydrogen. At the top, near the famous cloud bands and the Great Red Spot, that hydrogen is just gas, the way you'd expect. But Jupiter is so massive that as you sink into it, the weight of everything above presses down harder and harder. Go down 1,000 kilometers, the gas thickens into something more like a liquid. Keep going. The pressure keeps climbing. And about 7,000 kilometers down, roughly 15% of the way to the center, hydrogen does something it can't do anywhere on Earth. It turns into metal. Under that unimaginable pressure, the atoms get crushed so close together that the electrons can't stay attached to their own protons anymore. They break free, and they start roaming, drifting through the whole mass, shared between all the atoms at once. And that, a sea of nuclei with electrons flowing freely between them, is exactly what makes a metal. A metal. It conducts electricity. It's shiny. The lightest, simplest, gentlest element in the universe has become a vast, churning ocean of liquid metal, tens of thousands of kilometers deep, hidden forever beneath the clouds. And it's not just sitting there. Jupiter spins fast, faster than any other planet, a full day in under 10 hours. And as it spins, it drags that ocean of liquid metallic hydrogen around with it. You've got a conducting fluid, moving, churning, swirling. And when you move a conductor like that, you generate a magnetic field. This is the same basic principle as the dynamo in a power plant, except the dynamo here is the size of a planet. That's where Jupiter's magnetic field comes from. And Jupiter's magnetic field is terrifying. It's the strongest of any planet in the solar system, thousands of times stronger than Earth's. It's so powerful that it traps radiation into belts so intense they would kill an unshielded human in hours, fry spacecraft electronics, and it stretches out behind the planet in a tail that reaches all the way out past the orbit of Saturn. All of it. Every bit of that invisible violence, generated by an ocean of metal made from the most ordinary atom in existence. We have tried to make metallic hydrogen here on Earth, briefly in labs, by squeezing tiny samples between diamonds at pressures higher than the center of the Earth. The results are difficult, fiercely argued over, fleeting. We can barely make a speck of it for an instant. And Jupiter has an ocean of the stuff, light years of pressure deep, that's been churning quietly for 4.5 billion years. The most common element in the universe, wearing a disguise we can barely reproduce, running the machinery of the largest planet we've got. Number 4. Ice that is hot and black. Everybody knows what ice is. Water gets cold. It freezes. You get a hard, clear, cold solid. You've held it 1,000 times. So let me tell you about a kind of ice that is black, that is hotter than the surface of some stars, and that is, at the very same moment, both solid and liquid. And it may be the single most common form of water in the entire universe. It's called supersonic ice, and to understand why it's so strange, you have to remember what a water molecule actually is. 2 hydrogen atoms stuck to 1 oxygen atom. In normal ice, those whole molecules lock together into a rigid crystal lattice. They stay intact, just frozen in place, each little H2O holding its shape. That's the ice you know. Now take that water and do something violent to it. Crush it under enormous pressure and heat it to thousands of degrees at the same time. You would think heat plus crushing pressure equals some kind of hot, dense liquid. But that is not what happens. Instead, something splits. The water molecules come apart. The oxygen atoms, big and heavy, lock themselves into a rigid crystal grid, a solid cage, frozen in place. That's the ice part. It's genuinely solid. But the hydrogen, the smaller, lighter part, does not freeze. The hydrogen breaks loose and starts flowing through the cage of oxygen, moving freely, streaming through the lattice like a liquid running through a sponge made of stone. So it's solid and liquid at once. The oxygen is frozen. The hydrogen is flowing. A single substance, doing both things in the same place at the same time. And because of all that free-flowing charge moving through it, it doesn't look like the clear ice in your glass. It's black, opaque, and it's blisteringly hot, thousands of degrees, hot enough to glow. For decades, this was a prediction, a thing the equations insisted should exist. Then, in 2019, a team at a national laboratory in California finally made it and managed to photograph its structure, using lasers to flash compress water for a few billionths of a second, just long enough to catch it forming this bizarre crystal and confirm it was real. They gave it a name, Ice 18. And here's the part that recalibrates everything. Remember Uranus and Neptune, our ice giants from earlier? The conditions that create supersonic ice, that exact combination of crushing pressure and searing heat, are precisely the conditions you'd find deep inside those planets. Which means the interiors of Uranus and Neptune may be vast, thick shells of this stuff. Black, hot, half-frozen, half-flowing ice, making up the bulk of 2 entire worlds. And it doesn't stop there. The galaxy is full of ice giant planets. We keep finding them around other stars, by the thousands. If most of them have interiors like this, then this strange, black ice, this substance that breaks the simple solid or liquid rule you learned as a child, isn't the exception. The clear, cold, ordinary ice in your freezer might be the rare kind, and the real, common, default form of water across the universe might be a thing you've never seen, that's hotter than a flame, dark as coal, and frozen and flowing all at once. Number 3, the largest ocean in the universe. Water's the most ordinary thing in your life. It comes out of the tap. It falls from the sky. It makes up most of your body. There is nothing exotic about water, which is exactly why this one is going to do something strange to your sense of scale. 12 billion light years away, there is a quasar. A quasar is what you get when a supermassive black hole is feeding violently, swallowing huge amounts of gas, and that gas, as it spirals in, heats up and blazes so brightly that it outshines entire galaxies. This particular one has a name that is not built for poetry. APM 08279 + 5255. The black hole at its heart is around 20 billion times the mass of our sun, and it pours out as much energy as 1,000 trillion suns. And wrapped around all that violence, astronomers found water. Not a little water. Not a planet's worth. They found a cloud of water vapor so large that it contains, by their estimate, about 140 trillion times all the water in all the oceans of Earth. Combined. Every sea, every drop on our entire planet, multiplied by 140 trillion. Take a moment with that number, because the human brain is not built to feel it. You can say it, 140 trillion, but you can't picture it. And that's the point. All the water you have ever seen or imagined, every ocean, every rainstorm, every river, the whole blue surface of our world, is not even a rounding error next to this. It's the largest reservoir of water ever found in the universe, by a margin that makes the word largest feel small. Now, I should be honest with you, the way a good friend would. This water is not a giant blue sphere floating in space. It's vapor, spread incredibly thin across a region hundreds of light years wide. In any given patch, it's barely there at all. It's the total, summed across that unimaginable volume, that gives you the staggering number. So don't picture an ocean. Picture a faint mist, filling a space so enormous that even at near nothing per cubic meter, the grand total dwarfs every ocean that has ever existed. But here's the detail that actually matters, the one that should stop you. This quasar is 12 billion light years away, which means the light we're seeing left it 12 billion years ago, which means we are looking at it as it was when the universe itself was young, only about 1.5 billion years old. A baby. The cosmos had barely started. Stars and galaxies were still figuring themselves out. And already, out there in the deep past, there was more water than we have any right to expect. We sometimes tell ourselves that water is precious and rare, that Earth is a lucky blue jewel in a dry and hostile cosmos, and our water is precious to us. But the universe was apparently making oceans, on a scale we can't even hold in our heads, almost from the very beginning. We are not a drop of water in a desert. We're a drop of water in a flood that started before the earth, before the sun, before almost everything. And it's still out there, falling in the dark, 12 billion years away, a mist the size of 1,000 galaxies. Number 2, the strongest material in the universe. I want you to think about the strongest thing you can imagine. Steel, titanium, diamond, the hull of a battleship. Now throw all of it away, because none of it even registers next to what we're about to talk about. The strongest known material in the universe has a ridiculous name. It's called nuclear pasta, and it is so far beyond anything in your experience that the only honest reaction is to laugh and then feel slightly afraid. To get to it, you need a dead star. When a star much bigger than our sun runs out of fuel, It collapses. The core falls inward so hard and so fast that it crushes itself into something almost incomprehensible. A neutron star. Take something more massive than the sun and squeeze it down into a ball about the size of a city, 20 kilometers across. The matter inside is so dense that a single sugar cube of it would weigh about as much as a mountain. A teaspoon would outweigh every human being on Earth added together. Now zoom in on the crust of that neutron star, that outer shell. Down there, the matter is being crushed by gravity beyond anything we can produce, and the particles inside, the protons and neutrons, are caught in a desperate tug of war between forces. They want to push apart. They're being forced together. And so they compromise, and they arrange themselves into shapes. They get pressed into long tubes, like strands of spaghetti. They get squeezed into flat sheets, stacked up like lasagna. And the physicists who study this, with their wonderful sense of humor, looked at those shapes and called the whole thing nuclear pasta. And in 2018, a team of scientists ran the largest simulations ever done of what happens inside a neutron star's crust. They wanted to know how strong this pasta actually is. How hard would you have to push to break it, to deform it, to make it crack? The simulations were so demanding, they ate up the equivalent of 250 years of computing time on a normal machine. And the answer came back. Nuclear pasta is roughly 10 billion times stronger than steel. 10 billion. Not 10 times. Not 1,000 times. 10 billion times stronger than the strongest structural material we build our world out of. It is, as far as we can tell, the strongest material that exists anywhere in the cosmos. Nothing we know of comes close. The only thing in the universe that might outdo the crust is the even denser, even stranger core of the same star, just below it. And here's the quiet, eerie part. Because this stuff is so impossibly strong, the crust of a neutron star can hold its shape under almost unbelievable stress. But not infinite stress. Sometimes the strain builds up too far, and even nuclear pasta gives way, and the crust cracks. A starquake. And when a neutron star's crust shifts, it can send out a pulse of energy, maybe even a ripple in space-time itself, that we could one day catch with our instruments here on Earth. So somewhere out there, right now, are the dead hearts of giant stars, wrapped in a crust of the strongest material in existence, holding themselves together against forces that would erase anything else. And every so often, one of them flexes, and trembles, and breaks, and whispers across the entire galaxy. Number 1. The matter that could become everything. We've saved the strangest for last, and this one is different from everything that came before it. The iron rain, the diamond rain, the metal hydrogen, the black ice, even the strongest material in the universe. All of those are real. We've measured them, made them, photographed them. This last one we have never found. It might not even exist. And that is exactly what makes it the most unsettling thing on this list. Because if it does exist, it changes what the word matter even means. It's called strange matter. To get there, you have to go one level deeper than you've ever gone. Everything you know is made of atoms. Atoms are made of protons and neutrons. And protons and neutrons are made of even smaller things called quarks. Now, in ordinary matter, in everything around you, there are only two kinds of quarks doing the work. They're called up quarks and down quarks. That's it. Every atom in your body, every star, every planet on this list, all of it, built from up and down quarks. But quarks come in more varieties than that. And one of them is called, I am not making this up, the strange quark. Strange matter is a hypothetical substance where you take up quarks, down quarks, and strange quarks, and mix them together in roughly equal numbers into one dense, seamless soup. Not separate protons and neutrons, just quarks, all flowing together, packed to a density like the inside of a neutron star. And here's where it stops being a curiosity and starts being a problem. Back in 1984, the physicist Edward Witten put forward an idea that is genuinely hard to sleep on. He suggested that strange matter might not just be possible. It might be the most stable form of matter there is. More stable than the ordinary atoms you and I are made of. Sit with that, because it's bigger than it sounds. We tend to assume that ordinary matter is the natural, settled, final state of things. Rock, water, iron, flesh. Solid, permanent. But if Witten is right, then ordinary matter is not the bottom. It's a ledge partway down. Strange matter is the bottom. And that means everything around you, the chair, the ground, your own hands, is sitting in a kind of cosmic limbo. Stable enough to last billions of years, yes. But not because it's the lowest it could go. Just because it's never been given the push. And now, the truly disturbing part. A chunk of strange matter, a strangelet, if it's stable, wouldn't just sit there quietly. In theory, if it touched ordinary matter, it could convert it. The atoms it touches would collapse into strange matter too, joining the soup, releasing energy, and growing. And then, that bigger strangelet touches more ordinary matter, and converts that. A chain reaction. Matter turning matter into more of itself, spreading, the way ice spreads across a freezing pond. Some people have called it an Ice 9 scenario, after the science fiction substance that freezes everything it touches. Touch the world with one stable strangelet, the nightmare version goes, and the world stops being a world. So now you understand why people got nervous. When we started building particle colliders powerful enough to smash matter together at extreme energies, a few people asked the obvious, terrifying question. Could we accidentally make one? Could we create a strangelet right here and start the chain reaction on Earth? So let me bring you back down, because the answer is reassuring, and it's important. Physicists took that question seriously and studied it hard, and the conclusions are calming. For one thing, nature has been smashing particles together at energies far beyond anything we can build, all over the universe, for billions of years. Cosmic rays slam into the moon, into Jupiter, into everything, constantly, and none of it has turned into strange matter. The moon is still there. Jupiter is still there. We're still here. On top of that, the detailed physics suggests a strangelet's surface would likely end up electrically charged in a way that pushes ordinary atomic nuclei away instead of pulling them in to be converted. The doomsday version probably can't get started. And in all our searching, in all our experiments, we have never found a single strangelet. Not one. So as far as we know, it stays a hypothesis. A maybe. A strange idea at the very edge of physics. But I want to leave you with the thought, not the reassurance. Because that's where this channel lives, in the gap between what we know and what we can't quite shake. Strange matter may not exist. But if it does, then the solid, permanent, ordinary world you've trusted your whole life, the ground under your feet, the matter in your bones, is not the final answer. It's a long, lucky pause, a stable enough arrangement that has simply never met the thing that would undo it. We spend our lives thinking of matter as the floor, the thing you can stand on, the one thing that's just there. And the universe, quietly, at its deepest level, might be holding a different kind of matter in reserve. One we've never touched, that wants to be everything, and just hasn't started yet. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.